In this video, I'm going to work through problems on the worksheet number 1 for chapter 1. The first question is asking to draw the Lewis structures of a few compounds. The steps to drawing a correct Lewis structures are: start by calculating the total number of valence electrons. So for example, in this molecule HCHO, the total number of valence electrons are hydrogen is 1, carbon is 4, the other hydrogen is 1, and then oxygen is 6. So we have 6 plus 4, 10, 11, and 12. So we are looking at 12 valence electrons. So then the next step is to decide which one would be the central atom, and the rule is that the atom which the least electronegativity is the central atom, except for hydrogen. Hydrogen can never be the central atom. So here, keeping that in mind, carbon is my central atom because that's less electronegative than oxygen. And now we start by attaching hydrogen. So we have one hydrogen here, and then also remember that we have to fulfill the valencies of each of these atoms. So the best way to draw the Lewis structure for this molecule would be this way, where we have two hydrogens connected to the carbon, oxygen with a double bond to carbon, and then we have two lone pairs surrounding the oxygen atom. So always keep in mind the maximum number of bonds that each of the common elements can form. So there is an easy mnemonic you can remember as HONK, which H, that means hydrogen, can form 1 bond, oxygen can form 2 bond, nitrogen can form 3 bond, and carbon can form 4 bond. And then the last one you can write halogens, and halogens can also form only 1 bond. So if you keep this in mind, drawing correct structures becomes easier. Okay, the next one is CH3NO2. CH3NO2. So the total number of valence electrons, again, carbon is 4. There are 3 hydrogens, so that is 3. Okay, so 3 times 1 is 3. Then we have 1 nitrogen. Nitrogen has 5 valence electrons, and then we have 2 oxygens. So they will be 12. 2 times 6 is 12. So the total number of valence electrons we are looking at here is 12 plus 5, 17, plus 3, 20, 24. Okay, so we have to account for 24 valence electrons. So the way we would draw this is, again, keeping in mind the least electronegative atom should be the central atom. Here carbon. Then each of the hydrogen atom, they can form only 1 bond. So here are the 3 hydrogen atoms. Then we have nitrogen connected to 2 oxygens. However, if you keep it single bonded, then nitrogen's octet is not complete. So maybe one of the oxygen can be double bonded, and then draw out the lone pairs. So then make sure you count to that 24 valence electrons are taken care of. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So 24 electrons, and the Lewis structure is complete. The next one is HCN. Again, carbon is my central atom, being the lesser electronegative element, and since hydrogen cannot be the central atom, so you connect the hydrogen to the carbon here, and then triple bond to nitrogen and have a lone pair of nitrogen. So you can start by counting the valence electrons. Hydrogen is 1, carbon is 4, and nitrogen is 5. So this is a total of 10 valence electrons. So you can see that we have 2, 4, 6, 8, and 10 valence electrons here. Alright, so that's the first question. Next one is asking, the structure of cholesterol is shown here. How many pi bonds are present in this molecule? So to answer this, the easiest way is to look for double bonds and triple bonds. So remember, every double bond will have, if you have a double bond, it is made up of 1 sigma plus 1 pi. In a triple bond, we have 1 sigma and 2 pi. Okay? So in a double bond, 1 sigma, 1 pi, and in a triple bond, we have 1 sigma and 2 pi. So you can look at the mass structure and see whether we have double bonds and triple bonds. So we have, yes, we do have a double bond here. So that means we have 1 pi bond. So the answer to this question is it has got 1 pi bond. The next question is asking, according to the valence bond theory, which orbitals overlap to form the CO sigma bond and which orbitals overlap to form the CC pi bond? Okay, so CO sigma bond is this bond, the one which I'm pointing. That's the CO sigma bond. So for that, the best way is to put the lone pairs wherever necessary, like in this case the oxygen atom, and then figure out the hybridization of the two atoms. The easiest way to figure out hybridization of an atom is to count the electron clouds. So here, if you count the electron clouds in oxygen atom, it has got 4 electron clouds. Okay? So let me just elaborate this little portion of the molecule. So this is how it's bonded, hydrogen to oxygen and then to the carbon, okay, which is this one. And then we have 2 lone pairs. Okay, so that's the structure at this part of the molecule. So if you look, the number of electron clouds around oxygen atom is 1, 2, 3, and 4. So the oxygen atom is sp3 hybridized. Okay, so the oxygen atom is sp3 hybridized. Now what about the carbon atom? Okay, so carbon atom here, let's highlight that as a blue color. So this is the carbon atom. Okay, now this carbon atom is connected to an oxygen, another carbon, and then there is a hydrogen atom, right? So that oxygen atom is also, this carbon atom is also sp3 hybridized. So the carbon-oxygen single bond is resultant of sigma bond is formed by sp3 overlap, sp3 of which atom? Oxygen, and sp3 of carbon overlaps to form the CO sigma bond. And what about CC pi bond? So whenever we have a pi bond, the pi bonds are always formed by the overlap of p orbitals. Okay, so it's formed by the overlap of p orbitals. So to be more specific, you can say that the carbon p orbital and the other carbon's p orbital overlap. Okay. Now the next question is asking what percentage of p character is present in an sp3 hybrid orbital. Okay, so if you look at sp3, it is made up of s plus p plus p plus p. So in here, the s is only 25%, right? The p's are about 75%, so that's how the hybrid orbital is formed. The percentage of p character would be 75%. Right? So your answer would be 75%. Okay. The next question is asking you what is the hybridization of the oxygen bonded carbon atom in the following. So keeping in mind again what we talked about previously, this carbon, how many electron clouds are around here? This carbon has two electron clouds. Two electron clouds. So the hybridization should be sp. Alright. Next, propose structures for a molecule that meets each of the following descriptions. You have to draw a molecule which contains two sp3 hybridized carbons and two sp hybridized carbons. So we can draw the sp3 by having 4 sigma bonds. So if I draw a CH3 and then another carbon with say a triple bond to another carbon, okay, so that should give me the that should help me fulfill this condition that it has got oh sorry, no, it has to have two sp3 hybridized. So maybe I can put another carbon here, and again put a CH3. So if you look, the green carbon atoms, this one and this one, are sp3, and the blue carbon atoms are sp and sp. We did fulfill the condition that was asked. The next one is asking, draw a structure of a molecule which contains one sp3 and two sp2. So carbon atoms. So we can put one sp3 against CH3 and then two sp2. So we can have carbon with double bond to C, and then we can complete the valency by hydrogen atoms. So to draw this molecule better, the CH3, H, and H. So if you look, this carbon atom is sp2, this carbon atom is also sp2, this carbon atom is sp3. Count the electron domains around the central atom. This carbon C, it has got 1, 2, 3, so it's sp2. Here again 1, 2, 3, so it's sp2. And this carbon atom has 4 electron domains, which makes it a sp3. Then it's asking the next question as, write down the condensed electronic configuration of carbon, oxygen, sulfur, phosphorus, nitrogen, chlorine, and fluorine. I would suggest you please check the key that is posted. It's very basic from general chemistry, and I don't want to spend time working through electronic configurations. Next one is again asking you to draw the Lewis structure for acetone, which is the formula this one, and CH3NH2 methylamine, and identify all the bond angles, hybridizations, or electron geometries around every carbon atom and nitrogen atom. So let's draw the structure of acetone. Here we have a carbon atom, and there we have 3 hydrogen atoms, then another carbon with a double bond, and another carbon with 3 hydrogen atoms. So if you look, this is the structure of acetone. It's asking about identify all the bond angles. So the bond angle at this carbon atom, because it's sp2 hybridized, so we can write the hybridizations first. So this is sp2, this is sp3, this one is sp3. Okay. So the carbon, which is sp2 hybridized, has a bond angle of 120 degrees, and the electronic geometry is trigonal planar. And all the sp3 hybridized atoms have a bond angle of 109.5 degrees, and they have electronic geometry tetrahedral. So this is tetrahedral, and this one is trigonal. Now the next one is CH3 and H2. So again, keeping the rule that we have to complete their octets. Let's draw hydrogens with single bonds. Then we have the nitrogen, again the two hydrogens connected, single bonds. So this is the correct structure of CH3 and H2. And the electronic geometry around this carbon atom, because it's sp3, is bond angle of 109.5, and the geometry is tetrahedral. And this one is also sp3, and the geometry is also tetrahedral. Now finally, we are looking at the question number 7. 8, I would suggest that you again look into the textbook for the answers for this. Now 8 is again asking how many 7 is asking how many sigma and pi bonds are there. Again, remembering that if you have a triple bond, you have 1 sigma and 2 pi. You can say this one has 1 sigma and 2 pi. This one is a double bond, so it has to have we have to actually look at the total number of sigma bonds in the molecule, not just between the two carbon atoms, right? So this is actually not the correct answer, because we have to look at all the sigma bonds here. So if you can redraw this with drawing the bonds, this is how it looks like: H, C, triple bond C, and H. Now you can clearly see the sigma bonds. There's 1 here, 2 here, and 3. So 3 sigma and 2 pi. The way this should be drawn is carbon. Now we put bonds to the hydrogen atoms. You can see here again 1, 2, 3, 4, 5. So 5 sigma and 1 pi. This molecule has no pi bonds, all sigma bonds. But how many? So we have 1, 2, 3, 4, 5, 6, 7. 7 sigma. And this one, there are double bonds in it. So we should have pi bonds in them. Double bond C, double bond C. Here's hydrogens attached. Same thing here, hydrogens attached. So how many sigmas do you see? 1, 2, 3, 4, 5, 6. 6 sigma and 2 pi. Okay. Question number 8, I'm going to skip because you can check the answers in the textbook. 9 is asking what is the molecular formula of the molecule shown below. Every point in this structure represents a carbon atom. So if you redraw this structure, this is how it looks like: a carbon connected to another carbon, a fourth carbon, a carbon here, another carbon which is connected to this one. Okay, so there is a 6 carbon atoms in the hexagonal ring. Then you have a double bond to oxygen, and at the end of the chain where nothing is written, that means there's another carbon. Same thing here, we have another carbon. But the valencies of carbon atoms have to be fulfilled by drawing the necessary number of hydrogen atoms. So here if you look, this carbon has only 2 bonds, right? So it will need 2 more hydrogen atoms to fulfill its valence. Here again, same thing, this carbon needs 4 bonds. What about this carbon? It has got 1, 2, 3, so it needs only 1 more hydrogen to form the correct compound. This carbon will need 2 more hydrogens. This will need only 1. This will need 3 more hydrogens. And anything over here? No, because 1, 2, 3, 4. So it's complete. Now you can count all the carbons and hydrogens and oxygen and write down the molecular formula. So if you check the number of carbon atoms, we have 8 carbons, right? We have 8 carbons. See, 1, 4, 5, 6, 7, and 8. Oh, actually I forgot to draw the hydrogens here, remember? Every carbon atom's valence is to be fulfilled by hydrogen. So we have C8. Count the total number of hydrogens. We have 2, 4, 6, 8, 10, 12, 14. 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, actually, sorry, I didn't see that there was a double bond here. Okay, so we need to erase these hydrogens because there is a double bond here. Right. So once the double bond is drawn, this carbon needs only 1 hydrogen, and this carbon does not need any hydrogen. So we have actually 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are only 12 hydrogens and then 1 oxygen atom. Okay. So that's the molecular formula of this compound. Last one, select the best condensed structure formula for the following. So this is a skeletal structure. The condensed structure for this one, the correct one is actually choice number 3. So if you look at, see there is a carbon connected to 2 CH3s, which is what its CH3 2 means. And then this is connected to a CH2, which is this one. That is connected to another carbon, and there are 2 OHs that are in parentheses. And then you have a CHO. So choice number 3 is the correct answer. That concludes our worksheet number 1. We will work out the second worksheet in the next video.